So in the last lecture, we introduced two operations on vector fields, the divergence and the curl, or div and curl for short. And we saw how to calculate those operations using vector fields. So we saw how we could think about the divergence as being kind of like the dot product of a vector del with my vector field f. And the curl was kind of like a cross product of del with a vector field f. In this lecture, we're going to talk about what the actual physical interpretation of divergence and curl are. Let's start with the divergence. So the divergence of a vector field is going to tell us whether the flow is diverging or converging on a point. So we can kind of visualize this as a flow in space. Again, we can always think about flows in terms of vector fields. And we could ask, is there a point in space where the flow is converging? Is there a point in space where all of the arrows are pointing in towards that point? Or is there a point in space where the flow is diverging, where all the arrows are pointing outwards from that point? Well, when we have arrows pointing out from a particular point, we say that we have positive divergence. And when we have arrows pointing in towards a particular point, we say that we've got negative divergence. That is, we've got convergence. To see this in a little bit more detail, let's imagine that we've got a vector field f, and it's going to represent a flow of water, for example. And I'm going to imagine putting into that flow a little wire cube. I'm going to ask, is there a net flow out of the cube or into the cube? Because that would tell me whether or not I've got a flow that's converging or diverging. So let's imagine what that would look like. So let's draw a little wire cube here. Let's give it dimensions delta x, delta y, and delta z. So let's set it up so that this side is height delta z, it's got a width of delta x, and it's got a depth of delta y. And let's imagine that we've got a flow coming in from the left-hand side, and we've got a flow leaving on the right-hand side. So my flow is going to be represented by a vector field f with components f1 I vector plus f2 j vector plus f3 k vector. So you can see that the flow coming in from the left-hand side here, it's moving in the x direction, so it's really the f1 component of my vector field. So the f1 component is the one that's relevant for flow moving in from the left. And of course, when we're looking at the f2 and f3 component, we're going to be looking at the flow coming in from below and the flow coming in from the front or the back of our little wire cube. So we imagine that our wire cube is completely hollow and the flow is moving through it. Now the first question we want to ask is, what is the net flow out of this wire cube given a flow from the left of f1 and a flow from the right of f1? Well, you can see that the net flow in from the left will be f1 times the area of this side. So this side is of area delta y times delta z. So it would be flow in f1 times delta y times delta z. So again, that's just the flow times the area. What about the flow out? That will be given by also f1 times the area. So I'm assuming that the rate of flow hasn't changed, it's just a nice smooth flow. It's not changing very much. And of course the area of my cube hasn't changed. So what's the net flow? Let's call it it's going to be net flow out will be flow out minus flow in. So in this case, since these two things are actually the same, it's going to be equals to 0. We have no net flow for a smooth or a constant flow. No net flow out. For a constant flow F. So to get anything interesting, we're going to have a flow that varies in space. So let's say that my flow in on the left is going to be given by F1 at the point X, Y, Z. Right, so it's coming in from the left. And the flow on the right-hand side is going to be F1 at X plus delta X, Y, and Z. So I haven't changed Y and Z, but I've moved over an amount X. I've moved an amount, or delta X, in the X direction. So the flow in is going to be F of X, Y, Z, and the flow out will be F1 X plus delta X, Y, Z. So in this case, we have a net flow. Let's see, we've got F1 X, Y, Z, delta Y, delta Z. And I've got X plus delta X, Y, Z. Multiplied by delta Y, delta Z. So what is now the net flow out? It's going to be, again, flow out minus flow in. Which will be the difference between these two things. So I'm going to have F1 X plus delta X, Y, Z, delta Y, delta Z, minus F1 X, Y, Z times delta Y, delta Z. So you can see that I can get a net flow out if I've got a difference in the rate of flow in from one side and the rate of flow out on the other side. Now you can see that I can make that net flow as big as I like by just making the area delta Y, delta Z bigger and bigger and bigger. Of course, if I put in a bigger wire cube, I'm going to have a larger net flow. What I'm more interested in is the total net flow out of my cube per unit volume. So I'm going to take my flow and I'm going to divide it by the total volume of my cube. So I've got the rate of flow, outflow per unit volume, will be the flow out divided by the volume minus the flow in divided by the volume. And you can see that's going to give me F1 X plus delta X, Y, Z minus F1 X, Y, Z divided by delta X. Now let's imagine that we take our cube smaller and smaller and smaller and smaller. So delta X is getting really small. So if we look at the limit of this outflow, net outflow per unit volume, as delta X gets really small, we've got the limit of this difference divided by delta X, which is exactly the definition of our partial derivative. It's the partial derivative of F1 with respect to X. Now I can do this in the other two directions, in the Y direction and the z direction, so to get the net outflow of water on all 6 sides. And you can see that that's going to be given by the corresponding partial derivatives in x, y, and z added together. But that's exactly our divergence. So you can see that the divergence is intimately linked with the idea of a net outflow from a particular region. Now we can also use that to think about sources and sinks in a flow. So if you imagine again that we've got our little wire cube placed into a river that's moving smoothly, then we're always going to have the same amount of flow in on one side and out on the other side. So the net outflow will always be 0. But then we could imagine putting a little hose into the flow so that there is water being kind of injected into the flow at a particular point. There's a source of water. If I put my little cube around that source, that hose, we're always going to be measuring flow coming out of the sides of my box. So we're always going to get a positive divergence when there's a source of water inside of my little wire cube. Correspondingly, if I was to put a hose into the river and suck water out of that, so I've got a sink of water, almost like a drain, then you can see that there's going to be a net inflow, that is a convergence or a negative divergence due to the presence of a sink. So divergence tells us about whether the flow is converging or diverging, and it tells us about whether or not there are sources and sinks in our flow. Let's take a little example of that. So we've got a vector field f equals to x squared I plus y squared j plus 0k. I've visualized it in this figure here, what that flow field looks like. Now let's see what the divergence looks like and try and show in the xy plane where we have our vector field with positive, negative, and 0 divergence. So the divergence del dot f, or I could write it as div f, is going to be the derivative with respect to x of the x component plus the derivative with respect to y of the y component plus the derivative with respect to z of the z component. And that was just equals to 0. So you see we're going to get a scalar 2x plus 2y. So we get a scalar, and let's look for where we get 0 divergence. So where is this div equals to 0? So that's going to happen when 2x plus 2y is equal to 0, which implies it's going to occur when y is equal to minus x. So let's sketch what that looks like in the xy plane on top of the figure I drew of the vector field. So here's my vector field. Here is the line y is equal to minus x. This is the line of 0 divergence. At every point on that line, the divergence of my vector field is 0. There is no net convergence or divergence of the flow along that line. Let's look for where in the flow we have positive divergence. So where do we have positive divergence? This will occur where del dot f is equal to 2x plus 2y is greater than 0. So that's going to give us an inequality for x and y. It's going to give us y greater than minus x. Likewise, we can ask, where do we get negative divergence? Where do we get del dot f equals to 2x plus 2y less than 0? So that gives y less than minus x. So these are inequalities. They correspond to the regions above and below the line y is equal to minus x. So they're actually indicated by the upper right and lower left corners of this figure here. So in this region here, we've got positive divergence. And in this region here, we've got negative divergence. And we can actually see why that makes sense. We've got a flow that is spreading apart. The vectors are sort of pointing away from each other in the upper right-hand side, and they're sort of pulling together in the lower left-hand side. So we've got convergence down here and divergence up here. Let's now take a look at curl and try and understand what the physical interpretation of curl is. Well, curl is going to tell us about whether or not our flow is rotating in space. So again, if we imagine our flow is represented by a vector field, then if I have a vector field that is rotating around in this direction, then I will have a curl that's pointing upwards. And if I have a vector field that's pointing in the opposite direction, I'll have a curl that's pointing downwards. Now, the way that we represent rotation in vectors is by using the right-hand screw rule. So it's a little bit like the right-hand rule. We use our right hand, we point our thumb in the direction of the curl, and our fingers are going to curl in the direction of the rotation. So here's my thumb pointing in a particular direction. This is the direction of rotation. So it's actually the same way that we would use a screwdriver. So if I hold a screwdriver in my right hand, and I rotate it this direction, then the screwdriver will move in the direction my thumb is pointing in. So we did exactly the same thing with vector fields. So you can see there's a rotation around in this direction. So if I use the right-hand rule, there's a rotation in this direction, so I'm going to be going upwards. Likewise, there's a rotation in this direction here, so I get right-hand rule, rotation this direction, pointing downwards. So let's see if we can understand why the curl tells us about rotations. And the way that we're going to do this again is to use the idea of a little tiny cube placed in a flow and ask, is the flow causing the cube to rotate? And we're going to do that by looking at the action of the flow along the sides of the cube. In particular, we're going to calculate the rotation rate caused by the circulation of the flow around the cube. So let's draw a little picture of what I mean by that. So I'm going to look at this from above. I'm going to look for rotation about the z-axis. So I'm looking from above at the xy plane. And so my little cube is going to be represented by a square from above. And this is its rotational axis. And we're going to ask if I have sides delta x and delta y. And this cube is immersed in a flow field given by f equals to f1 I vector plus f2 j vector plus f3 k vector. What is the net circulation around this cube? Well, we can imagine calculating up all of the flow around the cube. So I've got at this particular point, this is the point x, y, let's say. At this point, I've got a flow in the x direction. So I write down the component of my flow in that direction, and it's evaluated at the points x, y, z. I could look at this point. This is the point x plus delta x, so I've moved over by an amount delta x, y, z. Just ignoring the z component because we're saying fixed in z. Then I'm going to have a component of the flow in the y direction, and that component is going to be given by f2 x plus delta x y z. Now, as I'm going around my cube, you see I'm touching each spot, I'm touching each corner. So I've got the next corner up is going to be this corner here, which is the point x plus delta x, y plus delta y. And I'm interested in knowing what is the flow around the cube there, but I need to know what the flow is at that point. And the flow is going to be given by F1, which is pointing in the positive x direction. Since I'm interested in the circulation of the flow in the anti-clockwise or counterclockwise direction, then I can have a vector pointing from here to the left given by minus F1. So this vector pointing in this direction that way is going to be given by minus F1 x plus delta x, y plus delta y. So again, the reason I've got a minus sign there is because I'm pointing in the negative x direction. So what is the component of the flow in the negative x direction? It's minus F1, because F1 is pointing in the positive x direction. Let's look at the next corner. Right here. This is the point x, y plus delta y. And I have a vector pointing in the negative y direction this time. So it's pointing back towards my starting point. And that vector is given by minus f2 x, y plus delta y, z. Let's add a z in here. So again, we've got a minus sign there because I'm asking what is the component of the flow in the minus y direction. That's going to be given by minus f2. Okay, so now I have all the pieces I need to calculate the net circulation around this cube. So the net circulation is going to be given by it's going to be given by the flow along the bottom multiplied by the distance we've moved, delta x, plus the flow along this side times the distance, delta y, plus the flow along this side, which is minus f1 times this distance, delta x, plus the flow along this side, minus f2 times the distance. So we get all of these pieces here. So if we put this together to calculate the rotation rate about the z-axis, that is the circulation divided by the cross-sectional area of the cube, we'll get something like f2 x plus delta x minus f2 all over delta x minus f1 x plus delta x, y plus delta y minus f1 divided by delta y. So those look a lot like partial derivatives, and indeed when I take the limit of delta x, delta y, delta z going to 0, I get exactly the partial derivatives. Now there's a slight misprint in here that I've corrected in your notes, but not in mine. So this should be a 2, and this should be a y. So again, that's been corrected in your notes, but not in mine. So sorry about that. So that tells us the rotation rate about the z-axis. We can also ask what's the rotation rate around the x and y-axes. And so we'll move through exactly the same process as we just did and form, again, combinations of partial derivatives, and then we get the rotation rate about the x-axis and the y-axis and the z-axis. So again, let me just quickly correct in my notes. This should be correct in yours. This is F2. And this is y. So you recognize that this is actually exactly the curl of the vector field F. So we see that the curl gives us a vector that is got components that tell us the rotation about an axis in the x direction, y direction, and z direction. So it tells us whether or not the flow is causing rotations, infinitesimal rotations. So let's try and put this into action with another example. So I've got a vector field here, again in the xy plane. And again, I've plotted what that vector field would look like in this figure here. So you can see that it's got a particular flow pattern. So we would like to know what is the curl and what is the region, where is the curl 0 in the positive z direction and the negative z direction. Remember, of course, that curl is a vector. So when I refer to positive, negative, or 0 curl, I'm referring to the z component of the curl. Of course, I've got a flow in the xy plane, so I have to have a curl in the z direction, just like the cross product. So we have our vector field. Let's calculate its curl using cross product del cross f, which is I vector, j vector, k vector, partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, and the components of my vector field f are y squared, x squared, and 0. So the curl will be given by I vector times the partial derivative of 0 minus the partial derivative of x squared with respect to z, which is 0, minus j vector. I've got partial derivative with respect to x of 0 minus the partial derivative of y squared with respect to z, which is also 0, plus k vector times the partial derivative with respect to x of x squared minus the partial derivative with respect to y of y squared. So I get 2x minus 2y. So as promised, the curl is a vector with only a k component. It's only pointing in the z direction. Could be positive, negative, or 0, but it's only pointing in the k direction. And the reason for that is that my flow only depends upon x and y, and so all of my vectors are always directed in the xy plane. They don't have a z component. So let's ask, where is the k component of the curl 0? So where is the curl equals to 0? This will imply that 2x minus 2y is equal to 0, which will occur on the line y equals to x. So let's sketch what that looks like on my little plane here. That's going to be the line going from the bottom left-hand corner right up to the top right-hand corner. So that is the region, the location where the curl of f, which was equal to 2x minus 2yk, is equal to 0. Sorry, curl. Now let's ask, where is the curl positive and where is the curl negative? Again, when I mean positive and negative here, I'm referring to positive in the z direction and negative in the z direction. So you can see that the curl will be positive in the z direction when its k component is positive. That is when 2x minus 2y is greater than 0, which will happen when y is greater than x. And curl will be negative in the z direction when 2x minus 2y is less than 0. So that'll be when y is less than 0. So sketching what that looks like, we can see that this is the region where I've got curl negative in the z direction, and this is the region where I've got curl positive in the z direction. So remembering again our right-hand screw rule, we can see that when I've got a positive curl, so pointing our thumb in the positive z direction, I'm going to get an anti-clockwise rotation. So I get an anti-clockwise rotation like that. And when I have a negative z direction curl, I'm going to get a clockwise rotation. And you can see that those arrows do indeed seem to rotate around in the clockwise direction in the upper left-hand corner and in a anti-clockwise direction in the lower right-hand corner. So these correspond to the 0, positive, and negative curls in the z direction. We're going to conclude the lecture with an important vector identity that relates gradient and curl. The theorem states that the curl of any gradient of a scalar field is equal to 0. That is, if I have any scalar field phi and calculate its gradient, then the curl of that gradient will always be 0, no matter what phi is. So let's prove that and then talk about the implications of that theorem. So let's let phi be a scalar field. It's arbitrary. I don't know what phi is. So the gradient of phi is going to be the vector of partial derivatives. Now let's calculate the curl of the gradient. So curl gradient phi, or using the del notation, I've got del cross bracket gradient, so del phi. So again, let's set that 3 by 3 matrix up. I've got I, j, k. I've got the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. And then I've got the components of the gradient, d phi dx, d phi dy, and d phi dz. So let's calculate what this thing is. I'm going to get I vector of the partial derivative with respect to y of d phi dz. So that would be a second derivative, d squared phi dy dz, minus partial derivative with respect to z of d phi dy. So again, that will be a second derivative, d squared phi dz dy. And I can do the same for the rest of the components. So I've got d squared phi dx dz minus d squared phi dz dx plus k vector d squared phi dx dy minus d squared phi dy dx. So, you notice there that we've got a whole bunch of second order mixed derivatives, dy dz, dz dy, dx dz, dz dx, dx dy, dy dx. But we remember from the mixed derivative theorem that for pretty much all of the phis that we'll be interested, all of the functions that we'll be interested in this course, the mixed derivatives give you the same thing, no matter what order you take the derivatives in. So I can do d squared phi dy dz or d squared phi dz dy. They'll give me the same thing, which means that these two terms will cancel. These two terms will cancel. And these two terms will cancel. So I get 0 in every component. I get 0. 0i, 0j, 0k, or the 0 vector. So the way that we interpret that result is that a gradient is a field, a vector field, but it's a vector field that has no rotation. Remember, curl tells us about the rotation of a vector field, and the gradient has no rotation. So one way you can think about it is to think about the scalar potential, phi, kind of like a gravitational potential. The gravitational potential is, for the Earth, for example, is going to be lots of nested spheres. Those are the level surfaces of the gravitational potential. And the force is the gravitational force is just pointing perpendicular to those level surfaces. So it's just pointing inwards towards the center of the Earth. So here is the Earth. Here are level surfaces of gravitational potential. So these are surfaces of constant phi. I can draw gradient of phi. In this case, it's going to point inwards. And that's going to tell me the force, the gravitational force, backwards in towards the center of the Earth. And you can see that no matter where I am on that sphere, it's always pointing in towards the middle. It's converging, but in such a way that there's no rotation. There's no rotation. Now, we've referred to fields like that as curl-free or irrotational vector fields. And the gravitational force is an example of a curl-free vector field. In fact, any force that can be expressed as a gradient is a curl-free vector field. That's going to be really important because it means that if I have a field a vector field that is curl-free, its curl is equal to 0, then there's always some phi such that my vector field f is the gradient of that phi. There's always some scalar potential, we call it. Now that's a very important idea because it means that I can make calculations of work very simple for these cases, as we'll see in the next lecture.